So let me start. So I'm going to talk about some symmetry. So let me explain the model problem. The problem that I want to consider is a model problem. And so by this I mean that U is a C2 function. So so this is the equation that I wanted to understand. So you may wonder, there are so many equations I can write, but why this specific one and what is it? So some of you have seen this type of equation. Okay, so let me tell you, for example, the first instance where it comes. I'm sure all of you are familiar with the Sokolov inequality, right? Okay. So there is a Sokolov inequality or the Gagliardo-Nirenberg Sokolov inequality. So the Sokolov inequality tells you that integral over n or u to the power 2 star, that is 2n by minus 2 by that is greater than less than or equal. U square, and then you will have an optimal constant which I call it here, and this inequality holds. Compact circuit in Rn, and hence its completion, and hence Rn, which is basically the completion of CC1 with respect to this norm. This norm is this to the power square root. So the importance is that the functions here, you have a gradient is in. So once you have an inequality like this, then you can ask whether this equality. So when I can have a constant here, then I can put any constant which is smaller than that. Then also this will. So the sensible question is to ask what is the largest constant for which this inequality holds. Okay. So this S I am denoting as the largest constant so that this inequality holds. With that largest inequality, the question is whether equality is going to be achieved in this inequality. Okay. So it's another game to show that equality is achieved. In fact, there are functions in this space d12 of Rn for which is achieved. Okay. So what I want to say is that there exists a U in d12 of Rn which let me call it this equality goes. Now, for this U, okay, so for example, you can, once it holds for U, in fact, you can show that mod U is also going to be in that space. And so mod U also achieves the equality. That way, you can also assume that this U is going to be greater than or equal to 0. And then you can write down the corresponding Euler-Lagrange equation, okay, of this inequality. Are you familiar with what it is? All of you? Okay, I'll just indicate. So you have an inequality, right? Here, this S is the maximum, okay? Or in other words, what you're trying to do is gradient of U square divided by the integral of mod U to the power, say, I'll put it as this number as 2 star to the power 2 by 2 star. So you are trying to find the minimum of this, okay? Okay, so maybe then you can try the minimum. At the minimum, you know that the gradient is 0, right? You basically try to compute that in the form of directional derivatives. And that will give you an Euler-Lagrange equation that is basically going to be this. So what you can show is that the extremely here. No, here I will cancel. So the extremely U up to a constant. Solves the very one. So it's going to be, so that is one way these solutions are going to come. They are going to be the extremal of this Sobolev inequality. Okay. So now why this is so important? Okay. There are many problems. For example, so there are many problems. So the second, so the equation comes as a limiting problem for many So I have written something like a limiting. Okay. So I just want to tell, you see, there are many problems where the solution of that requires knowledge of this kind of a problem. I'll just tell you a well-known problem from differential geometry where the solution of this is going to play a crucial role. Okay. So
why here 3 is bigger than equal to 3?
Otherwise, it's n plus the embedding will be in L infinity. So, sorry, not L infinity. For bounded domain, it will be in LP for all t. You don't have a n is equal to 2. What you have is basically you take the Sobolev space H1 or that. You take a bounded domain, not an area. This is going to be in P of omega. Omega is bounded for all. So basically, I think instead of the optimal embedding is not to a Sobolev space, it's going to be what is known as the Orlik space. So basically, here it says that once you fix this, it has a power integrability. This is the maximum. When n is equal to 2, here what you will get exponential of some power of u. That's exactly. N is equal to 2, you have an exponential integrability. So the thing is, there are analogous things, but things are little different. Yeah. So the equation comes as the limiting problem. So I'll just explain you why this is required. Okay. So there are many problems which comes where this knowledge of solutions of this is needed. Okay. So I will give you one such example. What's known as the model problem. Taking that. So I assume that you know some geometric terminology. So let me take M the Riemannian manifold. So that means you have a manifold and there's a metric on it. Okay. So now there is what is known as the conformal metric. Okay. So let G tilde be a metric. It is conformal. So let G theta be a metric on M which is conformal to G, point-wise conformal. That means that gives us the same angle. So that means at each point, G theta is going to be a positive multiple of G. Therefore, you can write basically this G tilde is equal to a positive function into G tilde at X is going to be equal to some f of X into G of X, where F is going to be a positive function. Okay. So in our context, we are going to write that this is the specific form u to the power 4 by n minus 2. So now these metric, they have the curvature, what is known as the scalar curvature. So I'm not going to the detail what it is. So let me write this G scalar curvature. The scalar curvatures of G and theta respectively. Then they are related by the relation minus, this is the Laplace Beltrami of the manifold of U, plus there is going to be a dimensional constant here, and then the scalar curvature of the original metric U, that is going to be the scalar curvature of the conformal metric and U to the power. So one of the basic question was, for example, so given a metric with the Riemannian manifold M and G, okay. So can you get a metric conformal to G so that the scalar curvature of the other metric, the conformal metric, is going to be a constant. So this geometric problem, if you try to put it in formula like this, it is equivalent to solving a partial differential equation. Okay. So the question is, does there exist conformal metric so in this formulation, so this is equivalent to solving the PDE, that is minus plus so here will be a constant. That constant can be absorbed into U because there are two different powers here. And so if you can find if this PDE has a positive solution, okay, so you need it's a positive solution, then you can define the conformal metric like this into the 4, and then that is going to have a constant forever. So that is one important. So you can see that n plus 2 by n minus 2, this exponent is the same as what is appearing. Okay. So now that is fine, but so what is the big deal about it? Okay. So the question is, can we solve this kind of a partial differential equation? Okay. So assume that your manifold is compact. So one way to finding such a kind of solutions for such kind of PDE is by trying to find you can pose it as a minimization problem. Or in other words, what you can do here is that so you can try to find the quantity infimum of here integral G plus this Cn into integral of M divided by integral over m 2 star, where you can see that this 2 star is going to be 2n by n minus 2, and 2 star minus 1 is nothing but this. So you can have this. So this you can study this minimization problem. Okay, so let me call it as so infimum of the short notation some q of. Suppose you can show that this quantity is achieved, some q of u naught. Suppose it is going to be achieved at some point. It's not clear whether it is achieved. Then you can show that then u naught is solution of the PT. So what I wanted to tell you is that one way of finding solutions is by trying to find a minimizer for this quantity. So, so that is what we try to do.
What is the C?
Which one? That's a dimensional constant. So it's a fixed constant. It comes in this conformal version. So basically, what I wanted to tell you that this quantity, solving this equation, you can reduce to finding a minimum for this kind of a quotient. Okay, as u varies over, you can take C1 or it is in the Sokolov space. You can do that, and if this is going to be achieved, then u naught is going to be a solution of this. But finding proving that this has a minimum, that is a non-trivial task. Because the basic reason here is that you have this Sokolov inequality, which basically tells you that you take the Sokolov space H1, for example, on a compact manifold or a bounded domain with zero boundary condition. So this embedding into this fund L2 star, a continuous embedding, but this is never compact. Okay? This embedding is never compact. Because of that, you may not be able to. There is that the standard theory doesn't give you a minimizer for this kind of a minimization. Okay. But what one can do is that I can put a minus epsilon. Okay. And instead of 2 star, I can put a 2 star minus epsilon. Then there is a standard theory which shows you that you have an extremal. Okay. So you can get something like an extremal, which I call it as some u epsilon. Okay. And that u epsilon is going to solve some kind of a PDE, something which is related. So now ideally what you wanted to do is that take epsilon goes to 0. Then the question is whether this u epsilon will converge to some. Okay. So in fact, that was the first idea of Emabe. That is what he proposed. And he just wrote that u epsilon take the limit and then it will have a solution. Okay. But the difficult part is that when you take the u epsilon, if you take the limit, it will go to some u. This u could as well be 0. So what actually you will have that is a weak convergence here, and the weak limit could be 0. Or in other words, what you are familiar with little bit of functionalistic language. So you have a sequence u epsilon in a these are going to be in the Sokolov space H1, and then you want to see its weak limit whether it converges strongly. So it may not happen all the time. Okay. So what really happens is that if this goes to 0, okay. So what will happen? These functions u. Okay. So you can actually prove that this is your manifold. Then you will have a point. Okay. And these u epsilons are trying to concentrate at it. Basically, I can show that this u epsilon, these are going to look like it's approximately like some v of say some epsilon tilde input minus n minus 2 by 2 into some v of x minus this point is x naught. It's not. Okay, I'm in the assuming that I'm in the Euclidean space. Okay, it has to be justified some epsilon. It's something like a function. You have a basic function p, and this function looks like that function is basically concentrating. Okay. And what is this B? And where these solves? And if you are and B is good. So if you want to solve a Mabe problem or problems of similar nature where this kind of difficulties comes, you basically want to understand, because this lack of compactness of these kind of sequences, that basically coming from you have extremals of this Sobolev inequality, and that you scale it, and that is how all these difficulties are. Okay? So if you know all solutions of this type of equation, okay, then you know, for example, more or less how these kind of problems behave. Okay, so that is where that is the just heuristic picture why we wanted to do. Okay, that is what I wrote here as the limiting problem. Okay, so what happens is that many such problems where you have here the equation was something looks like this, Laplacian plus something small order, and this is the leading exponent. Okay, many such problems when there is a this kind of phenomenon appears, and the limiting problem, the main difficulty comes through some concentration of solutions of some problem which can be solved, and that lack of compactness comes through the solutions of these kind of. Okay, so that is why we wanted to understand this. Okay, and even this Mabe problem, finally the solution of the Mabe problem uses very crucially the knowledge of all the solutions of this equation. Okay, so there are a lot of effort, and but finally the message is that the extremals of this solution, or no, sorry, all solutions of this equation, that they are crucial. Okay, yeah.
So how do you identify the B from here?
Which one?
How do you identify the
B
from here?
So so that basically what you can only show that you see there is something called this U epsilon circle. Okay, so then basically what you can look at it, you have to look at the mass. Okay, so then you will see, you can identify there is some point in the limit there will be some mass. Then actually there is a result argument due to Uhlenbeck, which tells you that if there is some small mass, it contains the full mass of a what we call a bubble. And once that is there, then you rescale it, and then you try to subtract it from the solution, and the remaining thing will go to 0. Okay. So that is how you do the profile decomposition. And this is, since it is a minimizer, it will just 1. And there could be many other sequences of this, what are known as Palace-Mail sequences. When you do that, there will be, these type of, it is going to be a finite linear combination of such. Okay.
One bubble can form up or more than one?
Here, in this case, it is going to be 1 because it is going to be the minimizer. The energies are going to be the same, but they are going to be what are known as Palace-Mail sequences. Okay, so there you are going to have sequences here forming. Okay, one which is concentrating, another one may be concentrating here, and also it's possible that concentrating points also can move, and it moves towards. But the point is that then there has to be a relation between the speed of concentration and the distance, so that the energy gets separated. Okay, so I'm going away from my topic. So this is going to be the yeah. So that is the motivation for studying this kind of problem. So the question is, can we classify all solutions of the PD minus the classing of Q. So first let me, so the answer is known. So let me go step by step. For example, first, so I have seen that the solutions of one way of getting solutions of this equation as the extremals of the Sobolev. Okay. Now, if U is an extremal of the Sobolev inequality, it solves that PDE. Moreover, it is going to be in this space D12 of Rn. That means it is going to be this gradient of U square is going to be finite. Okay. So what I wanted to say is that if above U comes as an extremal of Sobolev inequality, then you have in addition U is going to be D12 of Rn, or you are going to have gradient of U square. Okay. So this is, if you are getting the solutions through that sources, then you will have this extra bound. That means it solves this problem, and also gradient also is in L2. Okay. So once you have this kind of a condition, and it's not very difficult to show that this will imply that U of x, you can write a constant by mod x over minus 2 for x, or even at origin you can write something. So we are going to right. So at infinity it behaves like the Green's function, the singularity of the Green's function. So if you have this condition, then you can get that. In fact, you can prove that they are going to be equivalent. Okay. So you are going to be this kind of. So now the first result, so there is a classification initially. So the theorem, so which can be due to data, and another problem is Gidas and Spruck. So what they showed is that if solves say minus Laplace over positive and ux constant by mod x over minus 2. Okay. If you have this decay assumption at infinity, then U is of the form ux is going to be equal to. So you can write as 1 by epsilon over n minus 2 by 2 and some v of x minus x naught, where v of x is going to be equal to, for some dimensional constant 1 plus mod x squared, and x naught is inequality Rn. So the point is that first you take this V, you can show that it is going to solve this equation. Okay. Now, if you can very easily check that if you have any solution of this, you can translate and dilate like this to a point and with some parameter epsilon. That is also going to solve it. So if you can find one solution, then you will be able to find an n+1 dimensional family of solution. That means you can translate and you can dilate. Epsilon is a positive parameter and x naught is. Okay. So if at all you can classify all solutions, it has to be up to this translation and this dilation. Okay. So what it says is that you have one solution of this equation, which you have to write an appropriate constant, and then all solutions are generated. So you have a very neat classification. Okay. So this is the so some remarks before going forward is, so the first the proof I have mentioned is from the data. I'm not going to mention what it is because I don't require that. So Obata's statement is actually a geometric statement. Okay, so classifying this is actually equivalent to a geometric statement, which tells you that if you have any conformal metric on the standard sphere SA with constant scalar curvature, then it has constant scalar curvature 1 if and only if it's constant sectional curvature. Okay, don't bother about it. So it's equivalent to a geometric statement. That is what Obata did. Okay, so we are not interested in that. We are going to be we are interested in kind of a more PDE kind of argument. Okay. So what we are more interested in is the argument of Gidas Nirenberg. So what Gidas and Nirenberg, what they showed that if you solves minus Laplacian of u is equal to u to the power n plus 2 by n minus 2 with u greater than or equal to 0 and say the decay at infinity, or you can put it as finite. Suppose you have a solution like this. What they have shown is that then u is going to be radially symmetric. U is, I wrote U, right? So that means I have a solution of this equation. What they show is that then U is radially symmetric. Radially symmetric. Okay? With respect to some point. Some point. No. What does it mean? So I have a point x0 here. Okay. Your V is going to be constant on all circles around. Or in other words, I can show that I can write it as this U of x. That I can write it as some phi of modulus of x minus x0, where phi is a function defined from 0 infinity to. So what is the advantage of writing like this? Since it is a one variable thing, then the PDE can be converted into an ODE. Okay. So then this ODE, so that Laplacian of this equation minus Laplacian of u to the power n plus 2 by n minus 2, that becomes an ODE, and it solves this kind of phi second derivative of plus n minus 1 by r plus e to the power n plus 2 by n minus 2. This is going to be equal to 0. That is going to be that. If phi satisfies this, you define like this, and then it is going to solve that equation. But you have to be careful when you are defining like this. And if you want the remaining resulting function u to be smooth, you see, it's like even in one dimensional, if you take it, you take it, this is going to be even, right? Basically. So if you want it is smooth, that means the derivative has to be 0. Otherwise, you are going to have sharp edges. So this also will imply that phi prime of 0 is 0. So now this is a second order ODE with one boundary condition. Okay. So of course it doesn't fall into your standard thing, Lipschitz, and because there's a 1 by r floating around. But however, you can do the same kind of ODE analysis and show that if you have so you have this axis and phi primes, suppose phi of 0 is here. So some alpha. You assume that phi of 0 is some alpha, then this problem is going to have a unique solution. Okay, and that alpha basically comes in your characterization as the parameter. Okay, so therefore you are going to get that this x0 you already found. Okay, so that way you are going to show that you will get a unique solution, and that unique solution is what I have written. That is what the proof. Okay, so the basic point I wanted to get here is that once you show that the problem is radial, then it's an ODE, and you can do that. Okay, so the crucial thing is that to know that it's an ODE. That is what the argument of Gidas and Nirenberg. So now the question is, so the question that we are interested in, and there are many conditions, or there are many contexts. For example, where we have this kind of an equation, but we don't have this kind of an energy assumption. Okay, so what we are interested in is basically.
So for all the phi of 0, we can solve that ODE.
Yeah. So you can write in the integral equation format, and then you can try to solve. So now the question is, can we prove this symmetry? Can we prove the symmetry without the decay assumption? Without the assumption that is Ux is basically 1 by mod x to the power n minus 2, or which is equivalent gradient of t squared. So when I indicate the proof, yeah, so the proof of Gidas is using what is known as the moving plane method. Okay, and I will explain what it is. And these conditions, or some of them, were crucial for that method to start working. Okay, or more precisely, for the plane to start moving. So if you don't have that, it is not clear how you are going to proceed and get this symmetry. Okay. So the question is, the question is, if you don't have any decay or this integrability assumptions, and can you get the same classification, or are there other solutions of that PDE which does not satisfy it? So that is where so the question was answered by Gidas and Spruck. So it's basically a symmetry result without any decay assumption on the solution. Okay. So the theorem is more general. So I will state directly I'm already taken 35 minutes. So I will state the theorem directly. Okay. So whatever so they are going to consider this equation. So the theorem is, they even consider solutions which are singular. Okay, so I'll come to it. So let and use it, say C2 solves minus Laplace of Q is equal to G of Rn minus 0. Okay. Where so you have this equation in Rn minus 0. Okay, so it's okay even if you are at 0, but you won't require it. Where you make some assumptions on G. Okay, so where G from 0 infinity to is non-decreasing. So G is non-decreasing. Then what are the, with G of 0 is equal to 0, and do other assumptions like G of t divided by e to the power n plus 2 by non decreasing. So G is non-decreasing, this is non-increasing, and there's another assumption that G of t equal to some constant time for all t large, for some p greater than or equal to n by n minus. Okay. So you have this. So you have a nonlinearity like this. Okay. So you can see that whatever u to the power n plus 2 by n minus 2, what I put before, it satisfies all these assumptions. Okay. For example, when you divide with this, it's going to be a constant. Okay, and clearly at infinity you have this bound and things like that. So everything, all these things are satisfied. So once you have this, So once you have this kind of a bound, then the conclusion is not the first. If so, I have written here that 0 would be a possible singularity of the solution. Okay. So if 0 is a non-removable singularity, of U, then U is radially symmetric. Right?
By 2, yes.
Which one? N by n minus 2.
G of t by t to the power
N plus 2 by n minus 2. Sorry. N plus 2 n by n minus. Can you see it? Now? Okay. So if 0 is a non-removable singularity of U, then U is going to be radially symmetric about the origin. That is expected, right? For example, suppose U is blowing up at the origin, for example. Then you can only be, see, it cannot be radial with respect to another point, right? So then it has to be infinity everywhere. So you can expect it. It's not really a thing. And if C is that, and second part is that if 0 is a removable singularity. Then U is radially symmetric. With respect to some x naught. So that is the. So there are other interests for this kind of stuff. So let me just make some remark. For example, I have put here dt by t to the power n plus what is it? It's the lower bound here. Okay. So you have this equation minus Laplacian of u. For example, you can put it as u to the power p itself. This model can. Okay. So I have a number here. I put that n by n minus 2. Okay. And you know that this holds in say Rn minus. So what happens when you include the origin? For example, you know, right? You cannot conclude anything in general. For example, you know the fundamental solution, which is harmonic, right? 0 in Rn minus, right? 1 by mod x to the n minus 2. But at the origin, can you do that same thing? No, right? So what you can, so what the difference is here is that in these two cases, for example, you can show that when p is greater than or equal to this n by n minus 2, then you have this equation minus the Laplacian of u to the power p in the sense of distributions. That means you take the distribution of Laplacian, it's going to be u to the power p. Okay. And when p is less than that, what you get is that what is the distributional equation which it will satisfy? It is going to be something like minus Laplacian of u is equal to u to the power p plus some alpha times some derived delta at the top. Okay. So the things which are under consideration, this guy is not going to come. So this is going to be, so there have been many works on these types of equations and trying to find the singularity and so on in the beginning of the 80s due to Lyons and then Veron and many others. And again, I was giving you the connection with Riemannian geometry, okay, and defining the conformal metrics. And there has also been interest. For example, you have the manifold and you remove a point and to define a metric there. Okay, and so that except at this point or 2 points, okay, you can define u to the power 4 by n minus 2 into the standard metric. And remaining metric has constant scalar curvature or prescribed curvature, except at one point. So in that context also, we are interested in these kind of singular solutions. And if I remember correctly, I'm not remembering the full statement. And whenever you do these kind of things, one important question is the new metric, whether they are going to be complete. And that question is connected to whether you have a, whether this equation is satisfied in the distributional sense. So these are some of the remarks. Okay. Okay, so now let us come back to this theorem. Yeah. So there is so this result I put is due to Caffarelli, Gidas and Spruck. And in the same paper, there is a result. In fact, that's a more serious result regarding the singularities of these kind of solutions. Okay. So I'll just write what it means. Okay. So I'm not going to prove it. So the theorem. What it means. So let n less than or equal to 3 in C2 alpha of the unit minus 10. Okay. And u solves minus the Laplacian of u in the conjugate. Then yeah, where G is in the previous, G is as in the previous theorem, then can be written as then u of x is going to. So you want to understand how it behaves near the singularity. Okay, so ux is going to be equal to, you can write it as 1 plus or some d of x. No, they should write d of mod x. A radial function. Okay, so it's going to be a perturbation of a radial function. Okay, radial function where what is v? Where v of r. It is going to, you have the solution which is given in the conservative. Okay, so at each r, then you have this sphere, and you just average the solution around. So v of r is going to be equal to the average over boundary of b0 r of u x. Maybe I can put d sigma. D sigma is the surface measure of the sphere. Okay, so you can just average that. So for each all you average, so that is going to be a function b. So it's going to be the, so the singularity is going to be like this. Okay, and in the case, special case of singularity, there are more information on b. Basically, you can get these things by finding the radial solutions of these kind of problems, those are pathology, and then you can have a precise characterization of the singularities and so on. So you see, there was I told you that these works were started in the beginning of 80s or late 70s, and then these kind of precise informations were there, except that they had these kind of informations and the natural singularity. And after that, there have been some results, and this paper gives you a more complete picture of the entire. Some of the results were generalizations of proved by other people, including Gidas. Okay, so these are basically the content of this paper of Caffarelli, Gidas and Spruck, which I wanted to talk about. And I'm going to explain the method of moving plane, and to prove that is how this symmetry is. So to understand that, you have first I have to tell you what exactly I mean by the method of moving plane. So in the simplest, I already mentioned that the Gidas and Nirenberg, they proved using the moving plane method, the solutions are going to be radially symmetric. I'll just show you that under this assumption, how do we do that? Okay. Then I will make the essential ingredients which they brought in to do it. Okay, and basically, see, to understand that, you have to know how the standard method works. So that's the. So of course, I'm not going to give you the exactly the same proof of Gidas and Nirenberg. Of course, they use this bound, and I will work with instead the energy, which is the equivalent thing. and that way it is much easy. Okay? So what I want to say is that many of these tools have been refined and improved over a period of time, and there are much improved versions of the arguments that are given in these papers. But I'm presenting it because it is aim is to present the Caffarelli's. Yeah. So once we have this theorem, then that also answers the question which I started with here. Okay. So if you have any solution of this without any further condition, then they are all going to be that functions which I wrote somewhere. Yeah, they are going to be like this. Okay. So that gives you a complete answer once you have that symmetry. Okay. So let me just start with going. So moving. So the initial result, the Gidas and Spruck, that is on the board. Okay, so we are in the entire space RL, so I will directly work with RL so that I can show you what are the things which we require in the case of this Gidas Spruck. So I am going to work with this equation. So let do minus the Gaussian of u to the power minus 2 in Rn and u greater than or equal to 0. Okay, so once you have this by strong maximum principle, you can immediately show that you are going to be strictly positive. So, and then I'm going to assume that get over Rn. So I want to claim that U is radially symmetric. Radially symmetric with respect to some exponent. So what I'm going to do is that, so I have my entire Rn. Okay. So I want to show that it is going to be symmetric about some point. Maybe suppose I want to show that it is symmetric about this point. Okay. Suppose I want to prove that it is symmetric about the origin. Okay. So that means what is the solution at this point and this equal reflection? What is it going to be? If it is symmetric, they are going to be the same, right? So that means I want to prove that it is going to be symmetric about this plane, right? Then it is going to be same as here and here. Now it is radially symmetric. So I want the solution to be symmetric about each of the plane passing through. Once you can do that, then that will immediately imply that the solution is going to be radially symmetric. Okay. Okay. So the idea is first start with kind of a plane. It starts from somewhere here. Yeah. So I will work with this kind of plane which x1 is equal to some constant. Okay. Or x1 is equal to 0. I wanted to show that it is symmetric with respect to this or somewhere here. Okay. And I can do that because any other plane you can apply a rotation and basically do the same thing, or you can repeat the same argument. So I will show that the solution is going to be symmetric only with respect to the x1 variable. Okay. So because of that, I am going to consider planes which are parallel to that x1 is equal to 0. So let me just start with some definitions. Okay. So for define omega down. Therefore, x in Rn. So this is okay. So suppose this is my lambda. Then I have a plane here. Okay. My omega lambda is now for x in omega lambda. You can define anywhere. Okay. X is, so I take an x here. I'm going to reflect it here with respect to this point. So this point I'm going to call it as x lambda. Okay. X lambda reflection with respect to the hyperplane. Hyperplane x1 is equal to. That means this one. That is the boundary of this omega naught. Okay. So you can write an explicit expression for this. So this is the only the first coordinate will change, right? So this point is say x1, I will write it as some x dash, remaining n-1 coordinate. Up to here it is lambda. So this distance is lambda minus x1. So this is a reflection. So you have to subtract this. So you this is going to be so x lambda is okay. So x lambda is nothing but 2 lambda minus x1, and then where x is going to be x1, x dash is in Rn minus. So on the hyperplane is going to be lambda x prime. Okay, so that is going to be the point. So now what I wanted to show here is that, so for, yeah, so I have this. So now I have a solution which is defined everywhere. Okay, so in particular it is defined in omega naught. Okay, so I'm going to define the reflection of those functions. That means I take a point here, I will reflect it here, I will take the value. Okay, so I'm going to define v lambda from omega lambda to r by v lambda of x is equal to v lambda of x is equal to where is v over here? Okay, u right here. And u lambda of x is equal to u at x. That means u lambda at a point here is the value of u in the reflected. So now assume that the function is somewhat radially decreasing, right? Then what do you expect between the values of v lambda and v? Which value is going to be? You take a point here, and suppose it is here. Suppose the function is radially decreasing. Then at the reflected point, it is going to be bigger or smaller? Bigger, right? Or in other words, if the result is true, the solution, yeah, so the statement is even more, I just wrote radially symmetric, and in fact, it is strictly decreasing also. Okay? Radially decreasing, that's also there. Right, 100%. Yeah, so if it is radially decreasing, if the results are true, then you can see that a value at this point is going to be bigger than or greater than or equal to value at this point, right? So that is what we expect. That is the first thing what we wanted to get. So So what I wanted to claim here is where x is lambda naught represents 0, or lambda naught such that e lambda is greater than all x when so that means that whatever we are expecting, and that is what I wanted to get. Okay, so let's try to see how to do. So first, we know that V solves. Sorry, I'm writing V lambda. So you know that minus Laplacian of u is equal to u to the power n plus 2 pi. Right? Now what is u lambda? U lambda is u at x lambda, that is 2 lambda minus x1. If you find the Laplacian in the x1 derivative only, it will change, but the minus comes twice. So you are going to have minus Laplacian of u lambda, that's also going to be also lambda. So now what about u and u lambda on the plane? What happens on this plane? What is u and u lambda? When the reflection is the same, right? So u is going to be equal to u lambda. Okay. So then also note that u is going to be equal to u lambda on boundary of lambda. So what we wanted to show, we want to show that u lambda is greater than or equal to u. Okay. Or in other words, I want to show that. So we want to show that u lambda minus u. I want to show that it's positive. So therefore, I want to show that its negative part is positive. Right? Now you know that a function u can be written as u plus minus u minus. Okay? So you can do that. Now u lambda minus u. Okay, so now the condition comes. U, I have assumed that in the gradient of u square is finite. Okay, and u lambda also going to be that. Okay, so you can believe me that you can use this as a test function in the definition of weak solution for this. Okay, and you can multiply in this region. Okay, and it is going to be 0 here, and you can integrate by this. Okay, so once you do that, you will get that integral of n. This is going to be gradient of u dot product. Maybe let me call it as this is going to be some. Here I'm going to do it here. Okay, so integral over omega lambda, then you will have gradient of u dot product gradient of p as equal to integral over omega lambda to the power plus 2 by minus 2 the same. And similarly, you can have the other one, that is integral over omega lambda gradient of lambda dot gradient of phi. That's going to be equal to lambda plus 2 by minus 2. So now you can subtract one from the other. So u minus u lambda. Okay, so u minus u lambda. So this is going to be integral of n gradient of basically u minus u lambda dot product with gradient of my phi was basically u minus u lambda, right? Or no. Or maybe I can do the opposite. U lambda minus u is equal to dot product with gradient u lambda minus u. It's negative one, right? And that is going to be equal to, I'm subtracting this from here. So you will have integral of omega lambda u lambda to the power this into lambda minus u. This is negative. Now here you see this you can write it as u lambda minus u plus minus its negative part. Okay, and the u plus and u minus, when you take the gradient, they will vanish, and then this is going to be basically minus integral over integral over modulus of gradient of lambda minus u minus square. And then here again there's a minus here. Okay, and whenever this is positive, it vanishes. So basically on the right hand side, I have to integrate on omega lambda. And I only have to consider where which is bigger. U is bigger than U lambda. This is then I have this U lambda over say n plus 2 by minus U this into there will be a minus sign will come here and then lambda this won't come. Fine. So this is going to be a negative quantity, right? Because U is greater than U lambda, right? So I could have written no. Yeah, negative is on both sides. Yeah, then I can cancel. So basically now what you do is so when you simplify this, you basically get here. So integral over omega lambda, and then you have modulus of gradient of U lambda minus its negative part. So that is going to be equal to integral over omega lambda intersection greater than lambda. In the complement of this guy will become 0, so it is material. Then you will have U lambda over n plus 2 by this minus U to the power. And then I have this U lambda minus Q. So what I can do here is I can divide with U lambda minus Q, and then I can multiply with with the sign.
No minus on the right hand side.
There is no minus. This time U lambda this into lambda minus Q. Yeah, earlier there was no minus here, right? So here now there will be a minus. Now you see this you will split it into plus and minus. So you will basically get that this is going to be equal to integral over omega lambda intersection U greater than U lambda. Okay. So you have this quantity. Let me call it as some A of x. A of x into. So when you cancel on both sides, you will get a minus here minus lambda minus U it minus. So this is what you where ax is going to be this kind of a constant. Okay. So now this is going to be t to the power p, right? Some x to the power p minus y to the power p by x minus y, right? So you can estimate it. So basically x to the power p minus 1 kind of thing, right? What is n plus 2 by n minus 2 minus 1? That is 4 by n minus 2. Okay. And u is bigger than that. So basically this u, basically, so now you can this ax basically you can constant into say u to the power 4 by n minus 2, right? Minus 1 is here, 4 by n minus 2. So when you put this information together, so finally what you will get is that integral of omega lambda modulus of gradient of lambda minus u is minus. Okay. That is less than or equal to you will get integral over omega lambda intersection lambda, and then you will have here u to the power, there will be some constant u to the power 4 by minus 2 this lambda minus u. Now what you do is that you apply the Sobolev inequality. Okay. So when you apply the Sobolev inequality here, so I want to apply the Sobolev inequality. So 2, I want to make it as 2 star, right? That means I want to multiply with n by n minus 2. So what is the conjugate of that? N by 2, right? So when you do that, so when you apply the Sobolev inequality here, you will have constant into integral over the, I'm not writing this domain. So when I put this n by 2, you will get u to the power, say, you will get 2 star, and you will get 2 by n, right? To the power 2 by n. And on the other side, you will get that this is going to be integral over u lambda minus u is negative power to the power 2 into, so that is going to be 2 star, and you will get going to get 2 by. This is good. Now I have stated Sobolev inequality in the very beginning. Okay, so there this quantity can be estimated from above by the gradient of this quantity, square of. Okay, so once I do that, you can see that. Maybe I will continue here. Okay, so I will write as a integral of omega lambda, a modulus of gradient of lambda minus q minus, that is going to be none or equal to some constant into this. I can put it as integral over omega lambda of u to the power 2 star. This into this, I can use the Sobolev inequality and write it less than or equal to again the same term. Right. Integral over omega lambda modulus of gradient of lambda minus just use the Sobolev inequality in this term. So now you can see that this term and this term are the same. Okay, you have an extra factor here, omega lambda. Okay. So now this is my plane, x1 is equal to lambda. I am integrating this u to the power t 2 star on the right hand side. Okay. So I assume that integral of gradient of u square is finite. Therefore, u is in L2 star. So this is an L1 function, u to the power 2 star. So what happens is that, for example, when you go to infinity, then that quantity will go to 0, right? So that means when I make lambda large, so here there is going to be a constant which does not depend on t. Okay? So I can make this constant so small such that c delta into the entire quantity is say less than half. Okay, so I can make it less than or equal to say 1 by 2 lambda minus q is minus or lambda lambda. Now this implies that this has to be 0. Okay, this implies that gradient of u lambda minus u minus is going to be 0. Okay, so this is possible only when gradient of u lambda minus u minus is going to be. Once gradient of u lambda, so that basically shows that this is going to be a constant. But you know that u lambda is equal to u on this plane. Okay, so therefore u lambda minus u is basically a constant, and it is going to be 0 here, so it has to be equal to 0. So that will imply that lambda minus u minus is going to be 0. That means greater than or equal to 0. U lambda minus is going to be greater than or equal to 0. Yeah, this is true for lambda large, or in some sense when lambda is greater than or equal to some lambda. So that shows that u lambda minus is greater than or equal to 0 for every lambda. So what I have achieved here is, now I have a function here, and I can have some number lambda not here, And after that, if you start any point here and I take the plane here, okay, and the function I have, I reflect it here. That means you take value here, this is bigger than this, right? So now you assume the situation of some symmetric thing, one variable, so something like this. So this will continue to hold until I reach this critical position, right? I want to see which is this point of symmetry. Right now, what I have seen that when I do it here, when I reflect it, this is bigger. I should be able to, if the idea of the picture is correct, then I should be able to go under this position, right? So if I am anywhere here, still the result holds. And the moment I cross this, it won't happen. Okay. So the argument is that, yeah, so what we do is that, so we know that when you reflect, the reflected portion is bigger when you start moving the plane at infinity. Okay, so here you can crucially note that I use the fact that this I can make it arbitrarily small. There I use the integrability of u to the power 2 step. Okay, but if I don't have any condition at infinity, I cannot do that, right? Because we don't know. First of all, I may not be able to integrate. Okay, so there are various problems. Okay, so here I crucially use the integrability. Okay, so the same thing. So you could do that. So in the next step in the moving plane is, so let capital lambda equal to for lambda naught r such that lambda of x greater than or equal to x. Well, maybe I should use a different notation. Lambda naught I already used. Lambda delta in R says that u lambda x is greater than or equal to for all lambda greater than or equal to lambda delta, and this has to be true. Okay, maybe I'll in mega lambda for all lambda greater than or equal to. So right now what I have shown is that I have some point here. Okay, and if you reflect on any point to the right of that, then this relation goes. That reflection portion is bigger than. Okay, so now I am collected. So I found some lambda now, which I have chosen says that this is small. Okay, so now I am going to collect all such things. That is going to be my capital lambda. That is, I am calling it lambda delta, and I have already shown that this set is non from the previous thing. Okay, so then lambda is so what we have done with the earlier argument is that the set is going to be non-empty. Okay, so now, so ideally, you see, if it is symmetric, I want to come and move at some point. That could be the infimum of this set, right? Now, if you want to find an infimum, what do you need? The set should be bounded from below. So, can you do that? So I have seen that, you see, there is nothing. I started moving the plane from infinity here when lambda is large. Okay, I can do the same argument. I can go to here minus infinity somewhere here. Lambda goes to minus infinity, and then I can do the same argument here, and I can get the opposite relation. That means if you start a point here, the reflection portion here is going to be bigger than here. Okay, for all lambda close to the negative point. So that will show that there are points after a certain state, they are not going to belong to lambda. Okay, so I'm just going to write that. So that is not empty. So yeah. Now similarly, with the plane from say x1 with lambda large negative. So earlier I was moving from here, now I start moving from here. Okay, similarly moving the plane for x1. Okay, we see that lambda is bounded from 0.
Yes, so here actually we can give the argument that if it is goes to infinity, then that integral will be small.
Yeah.
So we can form.
Yeah.
For minus infinity, how is that?
No, there I am not going to integrate on this. So what I do is, so this is 0 and I have here, right? Now here I am going to reflect it here. All the integrals are going to be here. So finally that, so this is going to be my omega lambda complement. Omega lambda, my definition was here. Now it is here. Okay. So all the calculations I am going to do it here. So the same thing will work. And you will see that same argument, you take a point here, the reflected portion here, it is going to be bigger. So in omega lambda, if you take any point here, reflected portion is small after some time. Okay, so that is the one. So you see that this set is going to be non-empty and it is bounded from below. Therefore, I can so lambda is bounded from below. So what we are. So this set is where I can move the plane and this relation hold that lambda is a non-empty set which is bounded from below. So it is going to have an infinity. Okay. So let me give a name. Maybe let lambda naught is equal to, or lambda bar is equal to infimum of. Okay. So that means I have this point here, lambda bar. Okay, that is going to be the infimum of this thing. What does it mean? If I take any point here and you take the plane and if you reflect it, the reflected portion is going to be bigger than or anything to the right of that. Okay, and this is the last point for which it is going to happen. So in that happens, then you what you expect? Then you expect that it is going to be symmetric in this way. Okay. So what? So my claim is that. Lambda bar is going to be same as rho. That means it is symmetric with respect to this plane. That means you take any point here, here, and they are going to be symmetric. So u lambda bar is equal to, or in other words, u at x lambda bar, that reflected portion is the same as. So this is the crucial step. Okay. Once you do that, then you know that it is going to be symmetric in one direction. Okay. For example, suppose you are in R2. So what you can do is that you can start moving so that you will find with respect to this is symmetric. Now in the another point, you can start moving the plane. You can find another one with respect to it. So that way you will identify the point of what is the center of symmetry. Okay. And then it's not very easy, difficult to show that it's going to be. Of course, you have to do it in every direction. It's going to be symmetric. Then to identify the center of the symmetry, you can just do in orthogonal directions and see where it is. Okay. So once you have this, then you are through. Okay. Okay. So how do you do that? So u lambda bar is going to be ux. So how are we doing? So first of all, what is obvious? So we know that for Ex here, now if lambda is greater than this lambda bar, that means here, then you know that the reflected portion is bigger, right? So then we know that u lambda of x is going to be greater than or equal to u of x for all x in omega, right? This is true for every lambda. Okay. Now this is what u lambda of x is, u of x lambda, and you can take the limit. Okay, and that is 2x1 minus lambda, right? You can very easily take the limit, and taking the limit, you will see that u lambda bar of x that is going to be greater than for all x n. So that means at this point, what you get that the reflection is greater than or equal to. So this much is there. Now what do we have to do? We have to show that it's actually going to be, if it is not symmetric, if it is not equal, what we are going to show is that this optimal position, this is no more the optimal position. You will be able to move the plane further. Okay, and that will contradict the definition of that lambda bar. Okay, so first you are. Now the question is, can we move the plane further from here? Okay, so how do we do that? So for that, again, the tool is just look at this u lambda bar minus. Okay, so you can look at this equation. So u lambda bar, say let me call it as some w of x. U lambda bar minus. Okay. Then what do you have? Then for x in omega, right? And then we know that omega of x is going to be greater than or equal to 0, right? And then what is the equation omega is going to, so w is going to satisfy minus Laplacian of w of x, that's going to be equal to u lambda bar x, that we know that u lambda bar to the power n plus 2 by n minus 2 minus u x, u of x to the power n plus 2 by, right? So you now you have that it is greater than or equal to 0. Okay, so that means it is superharmonic, right? Or if you want more precisely, if you are not satisfied, you want an equation like what I did before. I can even write it as this is something like ax into u to the power or x into w. A nice function. I can do that. Okay. So my w is going to satisfy a nice elliptic equation, and w is going to be greater than or equal to 0. Okay. And now if w is not identically 0, then you have the strong maximum principle fixing, and you can claim that either w is strictly greater than 0, and also you know that on the boundary this is going to be 0, right? And w is going to be greater than or equal to 0 here, and here the minimum is there. Fine. So you have the half lemma. What does it say? So it is positive here, it is 0 here, so it is increasing, right? So du by dx1 is, so what do you get? dw by dx1 is, it is increasing, right? Correct? Okay. Now what is this dw by dx1 is strictly greater than 0 at this boundary? Okay. So when you calculate this, what do you get? What is this w? Now look at that w of x is going to be u lambda bar of x. That is nothing but u at 2 lambda bar minus x1 x dash minus u at with that x1 x bar, right? And when I correct, right? So when I find the derivative, what do I get? dw by dx1. When I do that, here there will be a minus will come. So basically this on the plane x1 is equal to lambda bar. That is going to be minus 2 times du by dx1 on the same plane. So what you are getting from the, you know that dw by dx1 is strictly positive, and that the half lemma, and that gives you that du by dx1 minus 2 times du by dx1 is strictly positive, or that implies that du by dx1 is strictly negative. That means at this point, so this all happens if w is not identically 0, right? So that shows that at this point u is actually strictly decreasing. Okay, fine. Okay. So u is strictly decreasing here. So I have a critical position here. The information is that I'm having u is strictly decreasing here. Okay. So now again the idea is that, so earlier I was using that when you can start moving the plane, the crucial thing was to make that measure small in that region where we are integrating. Okay. So here also you can do that. So now here what you have to do is that you have to take a small region here so that this measure is small, and that integral of that u to the power 2 star here is as small as you want. And also you can fix some something here. It's a ball such that outside this also that integral of u to the power 2 star you can make it as small as you want. And now once you have this, and then you can go somewhere inside here on a compact set where I know that my W was strictly greater than 0. Okay, that means the U lambda was strictly greater than U on this compact set. And now these things are continuous in lambda. So you have to choose this line such that whenever you reflect along some lines to the other side, it is going to be positive here. Okay, and in the other things, you can use the Sobolev inequality and you can basically manage. Okay, so you use the positivity here, and this is basically coming from the strong maximum principle here. At infinity, you manage it with this kind of integrability over here. Okay? And that way you can prove it. I'm not going to write because it will take another half an hour if you write. Okay. So the basic thing is that because of the integrability, at infinity, I can somehow manage. By working on balls, its complement, the u to the power 2 star is going to be as small as you want. And then you have some room here because inside here that W lambda is strictly positive, and you can do that. And this also you keep it a small measure such that integral of u to the power 2 star in this region is also as small as you want. With that, you can manage it. Okay. So that is basically the idea what you are having. Okay. So that is the way you prove this theorem. Once you have that, you have the symmetry. Okay. So this you can see that I crucially use the assumption that this assumption, okay, or integral of mod u to the power 2 star is going to be finite. Okay. So now when it comes to this Caffarelli theorem, or even here without this condition, I don't have any of these two. Okay. First of all, I cannot integrate any of those things. Because it all will infinity, and you won't be able to make anything small. Okay, so how do we do? Okay, so that is where I'm just going to show you what exactly the essential tools in doing this. Essential schemes are more or less the same. Okay, but how do you manage this?
So that condition can be replaced by the only integrability of U star.
Yeah, yeah, that helps. So the proof, you see, I worked out it for this specific nonlinearity, but you could have done it with the G with the whatever conditions which I stated. Okay, more or less things will go. Things will be more technical. So you have this equation minus Laplacian of u is equal to g of u, and this is then Rn minus, and u is. So what I'm going to prove here is that first let me take the case u is, sorry, 0 is non-removable. So that means I have this here and I have this. So what he is going to do is, so you want to prove that the solution is going to be symmetric around this point. So again, we don't have any idea about this infinity what's happening. So the idea is that, so what you are going to fix fix a point Z. So for convenience, I'm going to take it as, or I will draw the picture somewhere here. Now I'm going to apply a Kelvin transform about that point, and I'm going to write V of x is going to be 1 by mod x to the power n minus 2 u of z plus x by mod x. So this is the function which I'm taking. So we know that u has a singularity only at the origin. So from this portion, the singularity can come when z plus x by mod x square is going to be equal to 0. Or in other words, x is going to be z by mod z. Okay. So this function is going to be, if this is the z, so this has to be 0 means z has to be, x has to be equal to minus z by mod z square. So z is here, so you are going to have, z is suppose near the origin. Z by mod z square, the modulus, it will be somewhere here, far away. Of course, it's going to be minus z by mod z square. Okay. Now, other singularity can potentially come from here. X is equal to 0, right? So basically, this function Vx, this is going to be singular at 2 points. The possibility is singular at one is at the origin here, that is because of 1 by mod x square n minus 2, and at the point minus z by mod z. In any case, what I am here, I will take this axis joining 0 and z. Okay. So what we are having is that, so we know that function is going to be, has no singularity except at these 2 points. Okay. So then the claim is that you use the moving plane. Okay. And I will tell you how do you use that, and you show that your function v is going to be axially symmetric about this line. You understood what I mean by that? I have an axis, okay? So you take the circles around that, okay? Then it is going to be symmetric, okay? So the claim is that this v is going to be axially symmetric about this axis joining 0 and z, okay? That we have to do the moving plane. Okay. So I showed before that there are a lot of difficulty to apply moving plane there, but here this Kelvin transform will help. You can intuitively you can see that there's a 1 by mod x to n minus 2. Okay. This is going to give you a decay at infinity, so you will be able to do this. So then V has singularities. Or possible singularities only at 0 and minus 5. So we claim that our claim is V is axially symmetric. Axially symmetric. V is going to be axially symmetric with respect to the axis. Joining 0. Okay, so how do we do for convenience and for imagining? And let me take again by rotation and everything. I can assume that Z is, for example, on my xn axis. Okay, so for convenience. Yes, let's assume Z is an axis. So then the picture is 0 is here, okay, and z by mod z square, it could be somewhere here or somewhere. Okay. Now I want to show that. So I have a vertical line. Okay. So I want to show that it is going to be axially symmetric. That means I have any circles around that, it is going to be constant, right? So how do I do that? So I have found a way of, we have done earlier to prove that something is radially symmetric. You start moving planes in arbitrary directions, right? So here I want to show that it is symmetric in these kind of directions. So what do I do? Do I have to move the plane like this? It is symmetric like this. I only have to move the planes like this. Okay. So that means I am taking directions which are orthogonal to that. Okay. And start moving planes perpendicular to that. Okay. So that means I have the z-axis here. Okay. I will just start moving planes which are what is the x dash plane here. Right? Directions in the x dash, they are the normals, and I will start moving. Okay. So I have something like this. I'll come like this, and it is going to be symmetric. Okay. So I only have to move the planes in directions which are orthogonal to this axis. That is in this case. Okay. So that means I wanted to move the planes. So one such case is exactly what x1 is equal to lambda. That is one like what we did before. That is one thing which we can do. Okay. Then yeah. B is axially symmetric with respect to the axis joining. So once it is there, basically B is U, and from there you can conclude that I leave it as an exercise that U itself is axially symmetric. Okay. So once you prove for B, you can get it for B. Just think about it. Okay. So here, what we want to do is that we want to move planes which are in directions which are orthogonal to this axis of symmetry. That's what we want. Now. So again, if you want to apply the moving plane, earlier I showed you that the first difficulty is to show that V lambda, when you reflect it, that is greater than or equal to B for all lambda large enough. Okay. So that is the one which I got it last time. There I used the integrability. Okay. So now here I don't have it. So what I am going to do? So I am going to look at this, but this function is going to have a nice behavior. Okay. So let's so that is what I'm going to capitalize. So I'm going to start with this Vx. Okay, so Vx is going to be equal to 1 by mod x to the power n minus 2 into u at z plus x by. Right? Now I can, so when x is large, x by mod x square, this is going to be very small. Right? So it's a small perturbation at z for x large. So I'm going to have an expand. You see, anyway, we wanted to move the plane from infinity. Right? That means so when x is large, this is going to be small. Okay. So basically, this is value of u at z, right? At this point. Okay. So this is going to, I get expanded 1 by mod x to the power n minus 2. I can do the Taylor expansion. So first you are going to use z plus use z gradient of u at z dot product with x by mod x square. Okay. And then plus square of this modulus of, right? That means order of 1 by mod x. So that is going to be equal to, I can write it as 1 by mod x to the power n minus 2 u of z plus gradient of u at z dot product with x by mod x square. Sorry, x by mod x to the power n plus order of 1 by. Or in other words, I have this in Caffarelli, this paper notation. Let me just write it as g of x is going to be equal to this. They call it as some constant a0 by mod x to the power n. And then I have plus sigma I is equal to 1 to n, some constant k I. Then xi divided by mod x, mod x to the power n. Then plus order of 1 by for x large. So you have an expansion. Now you can even differentiate V, and you can essentially see that it is basically coming from here. And you can see that you can write dV by dx. It's going to be basically minus minus 2 0 divided by say, you can put any xi. You will get xi by mod x to the power n plus. So this is of x to the power n minus 1, right? So you will get 1 by mod x square. You get this, and then you can, where is it? And then you will have d square v by inside dx. This is going to be equal to the order of. So this function v, which we have defined at infinity, they have this kind of behavior. And you look at that, this a0 is basically u of z. So you are basically going to have here with a0 is. So now the first thing is that once you have this explanation, you can see that at infinity, the 1 by mod x square n minus 2, okay, as x goes to, so you will have a good decay, then you will be able to move the pen. Okay. But you are not going to proceed exactly like what I did in the integral form. Here it is much simpler, basic calculus, just direct calculation. You can do that. So I will just indicate what we get it. Okay, so
So that v will be u times x plus z by z. It will be x plus
x by mod x square. I am taking the Kelvin transform x square. X plus x by mod x square.
because 0 is the basically singularity point. Right? So
Yeah. So this is going to be, so
X plus-
it will be a singularity when z plus this is going to be 0. Okay. So that means z plus or z is equal to minus x by mod x square. You invert it once again, you will get x is equal to minus x by. So maybe I would have taken z here so that 1 by z by mod z square comes here. Fine. Okay, so now let me just, since I don't have time, I have written down the calculation just to convince you. Okay, so let's. No, it's okay. Yeah. So the claim is. So there exists a lambda naught. So my notations are as before. Okay. So earlier I have defined omega lambda, u lambda, u. U is replaced by v. That's all. Okay. So there exists a lambda naught, say greater than 0, such that for all lambda greater than or equal to lambda naught. So you will have v lambda of x greater than or equal to x for x in. So this is exactly what we achieved last time using that integral of that mod u to the power 2 star is small. Okay, that one. Here basically what we are going to do is that this v is going to have an asymptotic expansion at infinity, which is basically like this. If you have something which has this kind of an expansion, then you can do a direct calculation and you can do it. Okay. But just to convince you, so I will just write 1 or 2 lines. Okay. So you can have v lambda of x minus v of x. So you can calculate that. So what is going to be? So I will just write this is going to be a0 by this is v at x lambda, right? Now v at x lambda. I'm interested in for large. So what is it? This is the expansion. Okay. So v lambda of x is v at x lambda. So all these expansion you will get x lambda, right? And now you remember x lambda, the ith coordinate are going to be the same as I when I is not equal to 1. And the first one is 2 lambda minus x1. Okay. So I can do that. So I will just write down whatever I have. A0 by mod x lambda over n minus 2 plus sigma I is equal to 2 to n ai divided by mod x lambda n plus a1 will be there, a1 and the first coordinate is 2 lambda minus x1 divided by mod x lambda or n. Okay, and then you will have terms like plus order of 1 by mod x lambda, and then minus the same thing instead of x is x. Okay, the only thing is that here all these things are going to be same. But let me just it's easy for me to see. 1 by mod x to n minus 2 plus sigma I square to 1 n k I psi by mod x to the power n plus order of 1 by mod x. So now I can calculate V lambda minus. Yeah, so let us make some observations. Okay. So I'm going to do the reflection, right? So this is my lambda. Okay. And I'm going to take an x here. And so x lambda is going to be here. So I assume that lambda is positive. Okay, fine. So which modulus is bigger, x lambda or x? Then mod x lambda is, right? And here it is going to be the same on the boundary, correct? Right? Okay, so you are going to have this relation that we can keep it. So yeah, so V lambda of x minus V of x. So that is going to be equal to, I will combine everything, I will get A0 1 by mod x lambda. This is just to convince you a sample coefficient. X lambda to the n minus 2 minus 1 by mod x to the n minus 2 plus sigma I is equal to 2 to n a I x I 1 by mod lambda to the power n minus 1 by mod x to the power n plus that last term, that is a1 into 2 lambda minus x1 divided by mod x lambda over n minus x1 by mod x to the 1. I hope my something similar. If there is some small minor mistake, please correct. Okay. So once you are then you have to do various things. I already observed that I had this. Okay. So I have this plane and I have x here and I have x lambda here. Okay. So the first case I wanted to consider this case 1. 2 times mod x lambda, that is less than or equal to. This is possible, right? For example, when you are coming close to this, it's not possible, right? But when you move away, for example, you, at some point you can even reach 0, and then so after certain, I'm considering x which are after certain steps. Once you have this, then you can estimate here these quantities. Okay, so you can just estimate these things. You can use this in you have this inequality and you have this trivial inequality here, and you can combine both and you can estimate. And I will just write what you get finally. You will get that. You get that V lambda of x minus V of x. That is going to be greater than or equal to a0 by mod x to the power n minus 2 plus order of 1 by mod x to the power. Okay. And this basically you can write it as some a0 delta by mod x to the power minus 2. This is going to be positive for when mod x is large. That can be achieved when lambda is large. This is form. So now basically you want to deal with some point somewhere. Okay. So that I will split into two. Yeah. Yeah, so now the remaining cases, so I can assume that the remaining case mod x is going to be strictly less than 2 times mod x lambda. You can calculate things and you can manipulate a little bit. 2x lambda greater than, so what you will get here is that say v lambda of x minus v of x. That's going to be greater than or equal to some constant c1. You will get mod x minus mod x lambda by mod x to the power n minus 1 minus some c2 divided by. Now you can see that, for example, you can compare here, there's an extra here one. So if you can show that now, if mod x minus mod x lambda, that is this quantity is greater than C2 by C1 into 1 by, then everything gets adjusted and then you are there. Right? So we only have to consider the opposite. Okay, so now here, so let's consider, this is the case, mod x minus mod x lambda, which is less than or equal to C2 by C1 1 by. Now what does this mean? So I can get some condition here. So mod x minus mod x lambda. Okay. So that you can, yeah. So 1 by mod x. So you remember this is lambda here, x is here, right? So mod x is bigger than lambda. So I can put here 1 by lambda. So I can put here, I can take here lambda into, then mod x minus x lambda, mod x minus mod x lambda. That you can get is greater than or equal to lambda minus x or x1 minus lambda. You will have x1 minus lambda. Okay. That is going to be less than or equal to C2 by. Okay, so you have this condition. So what does it mean? So this means where is x1? X1 is going to be, yeah. So this implies that x1 less than or equal to lambda plus C2 by C1. 1 by, right? Yeah. Yeah. So now the crucial observation is that I have a different expression for here. Okay. So dv by dx1, I have this expression. Okay. So I have an explicit expression here. Now I am in a, you see, when lambda is small, I am in a very small region. When lambda is lambda and plus a constant by 1 by lambda. Okay. So in this region, you can actually check this dv by dx1. You can put it and you will see that dv by dx1 is going to be strictly decreasing. Okay. So it is going to be strictly, so once it is strictly decreasing and it's a point if you reflect it, it is going to be. So that is the, so yeah, so you can find the small and so that when you reflect in some region here, it is going to be decreasing and that can also be. So basically, if you have this expansion and whatever for the derivative, once you have these two, then you can get the plane moving from infinity. So this doesn't require any integration or anything, and so it is direct calculation, and then you can do that. Okay. So once you have that, you can keep moving the plane. Okay. So once you keep moving the plane, then you will reach at some point as before. Okay. So now the question is, again, you can do some of the, you remember at infinity and all, I have been controlling various things. Okay. So those things can be managed basically with this kind of an estimate. And also you can do some comparison with some other functions. For example, if you are a lambda here, you can hook up a harmonic function here. So x1 minus lambda by mod x to the power. It is going to be harmonic. Okay. And this is also going to be 0. You remember when I reflected the optimal position, it was going to be 0 here. This is also going to be here. Then you can use the Hopf and everything, and you can even get some precise estimate for the gradient. Okay. And again, putting all these things together, you can basically have the picture. If you have in an optimal position, you will be able to find, after a certain stage, you will be able to find some regions like this, where the function is actually strictly decreasing. And then it is also possible that move from a little bit here, and you can basically do whatever I've been doing. Okay, but it is not written exactly in this form in the paper. Okay, so what they do is that instead of I took that infimo all those lambda. Instead, what they do is that you take all lambda for which the reflection is bigger, and they claim that that set is both open and closed. Okay, closed it appears, okay, because just pass to the limit, and it is open. When you do that, again it uses off and various things. The same thing, but it is written in a different way. Okay, so now the point is that when you start moving the plane, for example, here there is a singularity. Okay, this plane cannot stop before. Essentially, what the reason is that reflection cannot be the same because there are possible singularities. Okay, assuming that the solution is blowing up, then here it is smooth. It cannot be the reflection. Okay, so that infimo has to be here. This needs some justification. Okay, so that so which I am not going to touch here. Okay, so you can basically show that the reflection, they are not going to be the same. From if it is blowing up, it is quite obvious. So because of that, in this kind of singular case, when you move, that infimo has to be here. It has to move up to 0, and therefore you will get the symmetry with respect to the origin. But if this is a removable singularity, then what happens that this kind of obstruction may not come. So you may be able to stop somewhere here. Okay, you see, this may not be a real singularity. We don't know, right? Because it depends on the decay of u at infinity. 1 by mod x to the power. What was the solution? D of x is 1 by mod x to the power minus 2 into u of z plus x by mod x square. Okay. So x is equal to 0, and this blows up, but this can also decay. So it depends on, you don't know. Okay. So that in the other case, it's possible that the plane may stop somewhere before. And since I assume that this z by mod z square is non-removable singularity, the plane has to move up to here. So that is why you will get the symmetry about the origin. Okay. Yeah, so you will get, so now the point is that I started with an arbitrary point. I got that the solution is going to be symmetric about this. Okay. Now I vary these points. So I will get about every axis is going to be symmetric, and therefore it is going to be radially symmetric. Okay. So that's basically the idea. Okay, so my time is up, and I will stop here. And so the other proof is more involved. Okay, it's the difficulties are nowhere compared to this. It's at a different order because that's singularity classification. Of course, again, it's using the moving plane and using the Kelvin transform argument. You have to identify some directions where these things work, and that involves quite a bit of estimates from potential theory, and it's very complicated job. So if you are interested and if you are comfortable with things, you can see the paper. And I want to make one final remark. So here I proved all the singularity classification using the, there were two conditions, like G was bounded from 0 by a constant time t to the power that p, and also that g of t divided by t to the power n plus 2 by n minus 2 is non-decreasing, right? And that lower bound, that t to the power p, that was removed later on by some what is his name? Sandeep. Okay, so it's a paper in invention. It's a short paper, and he proves the same thing just under the assumption that g is going to be positive, and g to the power, that essentially gt by t to the power n plus 2 by n minus 2 is non-increasing. But yeah, it's the same thing. And he refines those two and these two and proves that. And just to conclude, and this, when you come to this equation minus the class and over plus 2 by minus 2, then we know all the solutions, just u is greater than or equal to 0. And when I remove u greater than or equal to 0, it is not true. There are solutions, all sorts of types of solutions. Okay, positivity you cannot get rid of. And another thing is that if you put here at u to the power p with p 1 less than p less than n plus 2 by n minus 2. So again, it follows from the same paper that when this p is greater than or equal to n plus 2 by minus 2, then there is no solution. But later on, there's a work of Chen and Lee. They give some different, somewhat in the same lines, but it's a much simpler proof in this context. Okay, and they prove that up to 1 less than p less than p, there is no solution for the positive solution. And again, the idea is the Kelvin transform and the moving plate, but they do define that. Okay, I think I will stop.